So what I was mentioning then was the theory for the production of homochirality in the fundamental molecules of life. And the idea was that, well, the material which turned into these molecules could have been at one region of this neutron star, which was emitting circularly polarized light. And that light in the far ultraviolet could cause photolysis of those molecules, destruction of those molecules. But it would destroy those molecules with the same chirality, a little bit greater or a little bit quicker than those of the opposite chirality of the light. So we would get, at the end of destruction of many molecules, because to get to this point here, we have to destroy molecules, okay? So we're getting at this point where we have more right-handed over left-handed molecules, but most of the molecules have been destroyed, both right and left-handed. So that leaves us with very little molecules at the end of this process. So that's one argument against such a theory. But another one is that, well, these molecules, if they were produced in space, they would somehow have to get onto the surface of Earth if life originated on the surface of Earth. So then we would assume that they came to Earth. If they weren't formed with the Earth, they came to the Earth through meteorites. But these going through the atmosphere would heat up, and that would imply that the two enantiomers of right and left would again become racemic. They would have the equal probability because of the heating up. And also, well, these molecules are within, maybe some of those within the meteorite could withstand the heat and not become racemic. But then remember, there's also the impact, and the impact is going to generate even more heat and more pressure, which could cause racemic. So in fact, they have looked at meteorites, and they have found amino acids in meteorites. And they do find in some of the meteorites, not in all of them, but very few of them, they find a different ratio of the two different chiralities, right or left-handed, of the different amino acids that they find within the meteorite. So it is possible, but it's a very small amount that they find. And it's different for different meteorites. Not all the meteorites have the same ratio. And there's a lot of question whether it could be contamination from Earth, you know, from the organic amino acids produced on Earth, which are always of a single chirality. So that theory has a lot of problems with it, but for a long time it was the most seriously considered theory. There's another one, which is that molecules could be, there could be a production of this chirality if the molecules of life, the fundamental molecules of life, originated on a clay surface, which had its own chirality, or not necessarily its own chirality, but a structure such that different, whether it's right or left-handed amino acids, would have a different affinity to the surface. So if life started on the surface, on the clay surface, then because of the particular affinity of that surface to the different right or left-handed amino acids, let's say the right-handed amino acids would be less attracted to the surface, so they would wash away, and the left-handed amino acids would stay on the surface because they have a little higher interaction energy with the surface, and therefore would stay around, and they would be incorporated into a future life. But then, of course, you would have to imagine that we could have surfaces in which both chiral selection would be favored. That means we could have surfaces which favored right-handed amino acids and other surfaces which favored left-handed amino acids. So we would require in this theory that life started only on one particular surface. because there's no difference between the Gibbs free energy, as I mentioned, of these different surfaces, if they just have different chirality. So they would expect it to be found in equal proportions, except maybe in some very isolated, localized region. So this theory also has its own probability of being incorrect. And it also requires a little bit more description of how life could have started on the surface of clays. It was also in favor at some time because clays were thought to protect these molecules from ultraviolet light. But as you know, that we need ultraviolet light, at least of a certain wavelength, in order to get life started and to proliferating and evolving. Now, as I mentioned before, the energies, let's say, of the right and left-handed amino acids are not exactly identical. There is a small difference, and that small difference is due to the weak force, which is parity violating. So that experiment was done by Wu in 1957. This is a picture of her, in which she took a cobalt atom and put it in a very strong magnetic field, and then looked at what is known as beta decay. So cobalt 60 here is radioactive, and it can decay into nickel. So we have the same mass number, but we change the proton number. Okay, so we turn a neutron into a proton in this case by the emission of an electron, and we also have to emit an anti-electron neutrino in order to conserve fermion number here. Okay, so we do this experiment, then we put cobalt, radioactive cobalt, in a very strong magnetic field, and the cobalt has a spin, and we look at the distribution of the electrons and, well, the antineutrinos. The neutrinos in general are very difficult to detect, so basically we detect the electron, and through conservation of momentum, angular momentum, we determined that there was a neutrino emitted. And it turns out that if you do the experiment, you find that the electron can go in both directions, not only one. So it can go in the opposite direction, but it does it only a very few times in beta decay. So that indicates that there's a violation of parity. So for the other forces, remember there are 4 forces of nature: the gravitational force, okay, the weak nuclear force, the electromagnetic force, and the strong nuclear force. Now, in terms of strength, gravitational is by far the weakest. So we set that equal to 1. The weak force is on the order of 10 to 25 times stronger than the gravitational force. And the electromagnetic force is 10 to the 36 times stronger than the gravitational, and the strong force, nuclear force, 10 to the 38 times stronger. These forces also have different ranges. For example, the gravitational force goes as 1 over r squared, so it goes out to infinity. And the same for the electromagnetic force. But the strong force and the weak force, the nuclear forces, have very short range. So they're mediated by very heavy bosons. Whereas the gravitational and the electromagnetic force are mediated by essentially massless particles. So they have an infinite range. So what I wanted to point out here is that all of these other forces, except the weak force, do not violate parity. Only with the weak force there is a parity non-conservation. So as you may have noticed, that these 2 amino acids here are really just mirror images of them, no? So this is parity. If there's a difference in energy, if they're not exactly degenerate in energy, then there's parity violation. And that comes about because of the weak force. But it's a very small component. Even though the weak force appears very strong with respect to gravitational force, it's very weak with respect to electromagnetic or the strong nuclear force. And the violation also is very small. So the combined effect of having a weak force and the violation being very small implies that the effect is really too small, and we would need some kind of amplification. So we could get a very small difference in the concentrations of these two distinct enantiomers, but the difference would be very small, extremely small, of the order of 1 in 10 million or something like that. And that would not be enough to give us the homochirality that we're looking for the origin of life. So this theory basically has ended, that there's not being too much work being done on this. They are trying to find out mechanisms for amplification. So starting with a very small difference between the two left and right-handed concentrations to see if we could get some kind of catalytic effect, which would cause an increase in one over the other. And there have been some, I should say there are some experiments which have shown that there can be a catalytic effect, which is helping to increase the chirality, but it's only for very specific reactions, and its effect is also very small. So it's also very doubtful that this is the reason for the homochirality in the fundamental molecules of life. So we need a new theory. So in this new theory, maybe we should ask first, where on Earth do we have the greatest amount of circularly polarized light? And it turns out that where you can find the greatest amount of circularly polarized light is at the ocean surface, very close from below the ocean surface. So how does that come about? Well, we have sunshine, which is penetrating the ocean surface, and it's reflected. It could be off a molecule, or it could be off a material substance which is in the water. And then after the first reflection, we get plain polarized light. So I lost my arrow again, but in this region here, we have plain polarized light. So the light is vibrating, the electric fields are vibrating in a particular plane. And now when this is totally internally scattered of an interface, for example, the ocean air surface, then we can get circularly polarized light. Now, the amount of circular polarized light depends on how close to the surface you are. But if you're very close to the surface, let's say within 100 microns, where we believe that life indeed started in this micro layer of the ocean surface, then we could get up to about 5% maximum circularly polarized light. And that 5% is in fact the maximum where we are going to find circularly polarized light on Earth. Okay, but now the interesting thing is that if you're looking at the light from a particular direction, it is different. Circular polarization is different in the morning when the sun's over here than it is in the afternoon when the sun is over here. It could be, for example, left in the morning and right in the afternoon. Okay, right, circular polarized light. So that is interesting because there is also another breaking of the symmetry when we go from morning to afternoon. We know that the ocean surface is cooler in the morning than in the afternoon, because water is a good absorber of energy, and so the temperature starts to go up and it keeps that energy, particularly at the surface. So that is what's breaking the symmetry, that even though we get both left and right-handed circularly polarized light, turns out, let's say from this particular vantage point or viewpoint, that in the afternoon we get right-handed circular polarized light. a little bit more, like 5% more than left-handed, or 5% circular polarization of the whole system, because the rest doesn't necessarily have to be circularly polarized. In fact, it's not. No, it's plain polarized or unpolarized. So taking that fact into account, that we can have circularly polarized light at the ocean surface, then is there a possible way to explain this homochirality? And we have done that now to this, what we call the ultraviolet and temperature-assisted reproduction, or UV-TAR, of RNA and DNA. You know, at the beginning of life, there didn't exist all these complex enzymes, which are now needed in order to reproduce or replicate RNA or DNA. So the replication at the beginning would have had to be done through physical means, to the environment. And as I mentioned in another talk, the ocean surface temperature at the origin of life was high, let's say 85 degrees centigrade, and it was cooling throughout the Archean. So as soon as the ocean surface temperature went below, let's say 85 degrees centigrade, which is the denaturing temperature of short strand or intermediate strand DNA, then if we had these segments floating on the ocean surface produced through dissipative structuring from molecules like hydrogen cyanide and carbon dioxide, then at a temperature below the denaturing temperature, we would get this double strand, and it would stay fixed together, and we wouldn't be able to denature. But we know that the ocean surface temperature in the afternoon increases about 3 or 4 degrees centigrade in this micro layer of 100 microns from the surface of the ocean. And we also know that from the sunlight, we have ultraviolet light. At least during the Archean, we had this ultraviolet light at around 260 nanometers. So this ultraviolet light can be absorbed on DNA, and then the heat of deposition, the dissipation of the photon into heat, or proton transfer. We're going to stick with proton transfer. We'll see that in the next slide. But there's a mechanism, you know, we have studied in laboratory, that shows that with ultraviolet light we can denature DNA. In fact, it was one of the thesis of Ivan to look at how this denaturing due to UVC light depends on the pH of the solvent. Okay, and we also know that we have a hypochromism effect. That means that when the DNA is separated into single strands, it absorbs more ultraviolet light than when it is in double strand. So we get this increase in the absorption, depending on whether it's double or single strand. So even though the surface temperature would be below 85 degrees centigrade as we're going through the Archean, at least on the surface of the ocean, because of the heating due basically to infrared light, of water absorbing very strongly infrared light, we get the ocean surface warm, higher, about 3 degrees, and we also get the absorption of these ultraviolet UVC light in this DNA and causing it to denature. And then at night, when there is no ultraviolet light and no heating of the ocean surface cools and we can get extension. If we have magnesium ions, turns out that this extension goes forward without any enzymes. So this has already been shown in the laboratory. We showed that this happens in the laboratory, and this has been shown also, that we can have extension. As long as we have complementary pieces, they can come together and join one another. And they can, when the sunlight comes up again, they can form this phosphodiester bonds between these pieces. And we can have a double strand where we had single strand. So we form 2 double strands from a single strand, and that is replication. Okay, so this is interesting for us because it ties replication to dissipation of the photons. The more the dissipation of the photons, the greater the probability that we get denaturing. And the greater the probability of denaturing means the greater the probability of replication, because denaturing is the first step in replication. So therefore, we have replication tied to photon dissipation or entropy production, which is we are saying is the essence of life, is to produce entropy. But the interesting thing here is that also we're at the ocean surface, so we do have this component of circularly polarized light close to the ocean surface. So therefore, for example, if it's in the afternoon when the temperature is higher, so we are more likely to get denaturing through this UVC effect. If we have right-handed DNA, and since there's an extra component of right-handed circularly polarized light on the ocean surface, then the right-handed double strands are more likely to separate, denature, than the left-handed double strands. So because of the Gibbs free energy being the same for left-handed and right-handed, we would initially expect we had equal concentrations of the two. But replication requires denaturing, and denaturing is greater in the afternoon than is in the morning. And in the afternoon, there's an extra component of right-handed circularly polarized light, which will help further denature. So we get increased denaturing of the right-handed strands with respect to the left-handed strands. Okay. In the morning, of course, we're going to get some denaturing of the left-handed strands, but the surface temperature is colder. And this UVC denaturing effect depends on the temperature. So it will tend to be biased by what's happening in the afternoon when the surface temperature is warmer. So this is the experiment we did to look at UVC denaturing of DNA. We have the ultraviolet light and these fiber optics to bring the light into this region, which is a temperature controlled region. We control it by the computer, where we have a quartz cuvette with DNA in solution. Quartz so that the ultraviolet light can penetrate, because glass it doesn't allow the ultraviolet light to penetrate. And then we measure the absorption and the scattering. And this is our absorption that came out of that instrument, our apparatus, experimental apparatus. And we see the denaturing is a function of temperature because we have this hypochromic effect. Remember that as we denature, we go from double strand to single strand, we get greater absorption. This is absorption, basically absorption here on the left axis. This is for 25 base pair synthetic DNA. And so we get temperature denaturing. As we go to higher temperatures, you can see that the system is denaturing. And now we wanted to do that to see if we could, at a fixed temperature, so we bring the system, this is the case of salmon sperm DNA in pure water. We bring the temperature up to 40 degrees centigrade and keep it constant, that temperature, and then turn the UVC light on and off. And we see this is integration over 255 to 265 nanometers, where DNA is absorbing. So we're about here to here. We're just integrating over this region, okay, where it's the peak, and plotting the result, the integration, as a function of time of the experiment. And every time we turn the light off, we get the absorption goes down. We turn the light on, absorption goes up. So this is like UVC denaturing. We're denaturing. This is this hypochromic effect again. And this is the integration over the spectrum, but we can also look at the spectrums as a function of different temperature. We find that for double strand, we get an increase in the absorption. Okay, these are these curves, the positive curves. This is the difference between light on at the end of the light on region and at the beginning of the light on region. So we take the difference, and that gives us these spectrums, the absorption spectrum. This is for double strand, and for single strand, it doesn't do that, of course, and that's what we expect, and that's good news. But we do see a decrease in the absorption. In fact, it goes the other way around. And why is that? That's because we are producing some of these thymine dimers. So if you have two thymines together in the strand, for instance, they can form a covalent dimer, and that absorbs less. So we get a decrease. We don't have any thymine dimers, but we can also have covalent interaction between cytosine and thymine, for instance. So we can have other dimers which cause this decrease. And in fact, it was around 270 nanometers, which they have detected formation of thymine dimers, which do decrease the absorption. So this was just using double strand and single strand as a control to see if we can, in fact, to get double strand denaturing, and in fact we do. And then we can integrate it and plot it as a function of temperature and calculate what is the effective UVC denaturing rate in percent per hour as a function of temperature of the system, the DNA at a fixed temperature. So we look at the temperature and we measure the different spectrum, and that gives us integrating, gives us this effective rate of UVC denaturing. And as we get closer to the denaturing temperature, which for our case was about 80 degrees centigrade, then the rate of denaturing goes up very rapidly. So that is useful for us, and that's good for us, which is showing us that in the afternoon, when the ocean surface is warmer, we're going to get more UVC light denaturing of DNA in the right-handed. If the incident light, if the light at the surface was right-handed circularly polarized, then we would get more denaturing of right-handed DNA than we would left-handed DNA. And that allows us to replicate right-handed DNA, but not so much left-handed DNA. Okay, so what is causing that? Well, first we thought it might be that the energy of the photon is deposited within a certain volume. And if that energy is sufficient to raise the temperature by, let's say, another 3 degrees, remember we have already raised the temperature by about 3 or 4 degrees because of the infrared light from the sun on the ocean surface. So if we have another 3 degrees, then we have 6 degrees increase, and that is more than sufficient to cause denaturing. That is about the width of the denaturing curve for these short strand segments. So the idea was to calculate what volume, how many base pairs would fit in this volume in which the water, due to that single photon being absorbed on the DNA and then its energy being distributed in the water, how much the temperature would increase, or better said, what volume, what spherical volume would correspond to the energy deposited by one photon of 260 nanometers. And so we could do that calculation if you know the energy of the photon. It's about 4.8 electron volts. And if we know the heat capacity of water, which is given by this number, and then we calculate the diameter in which we get 3 degrees centigrade throughout the volume. And that diameter corresponded to 4.9 nanometers, which means about 16 base pairs. So that's about here. We have 16 base pairs in this model here that we're rotating. So that would correspond to about 16 base pairs. But the trouble is, so then we did molecular dynamic simulations. And that was my student Adriana. We did those calculations, and it in fact showed that the energy was very rapidly dissipated into the water. So in terms of picoseconds, no? So it was dissipated very rapidly from DNA and then passed to the water extremely rapidly. So it would be hard to imagine that you could have denaturing through these breaking of the hydrogen bonds in such a short time period. So what we realized is probably what's happening. It's not because of the heat deposition of the photons, the energy in the local region, but rather because we're getting proton transfer, which is another chemical or photochemical reaction which can happen. Besides, this is dissipation into heat to the conical intersection. In this, the heat deposition. But we can also have these very rare events in which we have a photon transfer from one of the bases, proton transfer, sorry, from one of the bases to another, due to the absorption of a photon. So for example, in this we have, this is guanine and cytosine. We have 3 hydrogen bondings here, and through absorbing of a photon, we can go so that the hydrogen gets transferred from this covalent bonding here on guanine to cytosine here. You know, so this one in the middle has transferred. When you have such an event like that, causes a change in the distribution of the charge on the system. And in fact, that change in the distribution weakens the system. So the reason that these 2 strands of DNA are bound to each other is not only the hydrogen bonding between them, but also the stacking interaction between pairs, one on top of the other, the base pairs. And if we get a change in the charge distribution, then we can have a change in the stacking interaction, which can cause debilitating of the structure. So that can cause DNA to denature. So that is what we now believe is happening in light-induced proton transfer, causing UVC-induced denaturing. Okay, so how does that lead us to homochirality? Well, as I mentioned, because of the different absorption coefficients for left and right-handed, and the fact that the effect of UVC light-induced denaturing is temperature dependent, we see in this graph, then in the afternoon, if we have only right-handed, or we have basically right-handed, or a component, I should say, of right-handed circularly polarized light, and if we look at what is known as the coefficient of left minus right, okay, so that's circular dichroism of DNA for left and right-handed. Here we're only plotting it for right-handed. We find that we get more right-handed light absorbed at about 257 nanometers, more or less here, no? This is the case for these different base pairs, these different strings of double-strand DNA. And this is the case here, bottom case here, is the case that we have DNA with an amino acid, which is tryptophan, which also absorbs UVC light. Now this here on this graph is actually 4 times greater, but it would fall off the graph, so we didn't put it here. So just the fact that we're having tryptophan connected to DNA increases the circular dichroism by a great amount. That means it increases the rate at which right-handed circular polarized light is absorbed on right-handed DNA with respect to left-handed circular polarized light. Now we should also take into account the spectrum of the light and also the spectrum of absorption, because it's not only absorbing, of course, at 260 nanometers, but through a wide range. DNA absorbs, as you know, from about 300 nanometers all the way down to about 220 or less, in which it starts ionizing. So we have to take into account the absorption and the sunlight, which is arriving at Earth's surface. So taking that little peak in the UVC, the sunlight, and doing the, so we incorporate that, and we, what is it called? I forgot what the name of it now is when we're doing this interpolation. So we have to include both of these structures, no? And that gives us these curves, okay, for these different strands of DNA, double-strand DNA. For the long strand, that's this one. The shorter strand, that's this curve. And for the shorter strand with tryptophan, it's this curve here. Or this is actually just pure adenine and thymine, double-strand DNA with tryptophan. That gives us this curve, which is actually 4 times steeper 4 times greater. The word I'm looking for is the convolution. So we do a convolution, okay? So we're multiplying these spectrums by these spectrums. So we have greater intensity where there's more light, and that's why it goes down farther here than in this graph. Okay, this is convolution of this circular dichroism spectrum with the light which is arriving at Earth's surface in the Archean, and also the absorption of DNA that gives us this spectrum. Okay, so with these curves, we can then calculate the emergence of how homochirality would have emerged through this UVC-induced denaturing. And we do that with a very simple equation, which is a recursion equation, which just specifies the number of left-handed DNA structures in a given generation, I, okay? It's equal to the number of left-handed DNA in the previous generation times 1 plus some factor, which depends on the probability of absorption, because remember to replicate, and this is indicating how many left-handed DNA we're going to find in the next generation. So this is replication. Depends on the probability of, for example, left-handed DNA absorbing a left-handed circularly polarized photon. Okay, so this is left-handed DNA absorbing left-handed circular polarized photon, and this is left-handed DNA absorbing a right-handed circularly polarized photon. So these are different probabilities. This probability is greater than this probability, but they're both non-zero. So we include them in this equation, this recursion equation, and we look at the number of left-handed as a function of time. We do the same for the right-handed DNA. Okay. C is some parameter which you can relate it to the quantum efficiency for denaturing. That means how many photons we need to denature a particular strand. So just taking as an example, C equal to 0.001, which indicates that we get denaturing after absorbing 1,000 photons. Okay, and so that is just some constant. It doesn't really matter what it is, but we can put it in and change it and play around with it. And including the amount of excess circular polarized light in the afternoon, which, as I said, is about 5% on the ocean surface. And that's maximum that you're going to find anywhere on Earth. And including this effect of circular dichroism, which is about 0.07% or 4 and 6,000. So that's here, that's how these DNA absorb right-handed with respect to left-handed light. Okay, and that's the difference is very small. It's only this less than 0.1%, but over many generations it can add up. So you can convince yourself that these are the probabilities. If we put the probability for a right-handed photon being absorbed on right-handed DNA being equal to 1, then you can convince yourself that these are the correct formulas for the probabilities of a left-handed photon being absorbed on a left-handed DNA, and a right-handed photon being absorbed on a left-handed DNA in terms of these parameters here. So now that we have these parameters,